Okay, let's analyze a problem that would be totally impossible to solve using any of the techniques we've learned so far in this class. We have to use conservation of energy to do this. Let's look at this roller coaster. You start out at the top of a big hill, roll down the hill, go around a loop-de-loop. Now, if you try to think about this using Newton's laws, it becomes fantastically complicated because it's like the slope problems we talked about, except that the slope has a continuously changing angle the entire time. Every instant of motion, that slope makes a different angle. So if you tried to analyze it using Newton's second law, you'd be drawing an infinite number of free body diagrams, each with a different angle theta. In other words, you'd have to use calculus techniques, and you'd probably have to use a computer to evaluate the calculations. This would be really hard to do by hand, and you need to know the exact formula describing the shape of that roller coaster track. Really complicated. But because gravity is a conservative force and the work done by gravity doesn't depend on the path you take, if we assume that this roller coaster is frictionless, then we can use conservation of energy and solve it just knowing the initial height and the final heights. That's all we need to do to analyze this problem. So let's set this up using our law of conservation of mechanical energy as we've been writing it down so far. We say potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. We have formulas for these things. mgy initial, 1/2 mv initial squared, mgy final, 1/2 mv final squared. There are m's present in all those terms, so all those m's cancel out. And I'm going to solve for v final. And you can see that in just a few lines of math, we're able to find the final speed for any final height. In particular, we could find the final speed at the top of this loop, we could find it at the bottom of that loop, we could find it at any point along this track, any point within that loop. All that matters is the height you started from at the top of the hill and whatever height you ended at. And all these details about the crazy curved path you take are irrelevant because this conservative force is path independent. So at the top of the loop, the final height is 2 times the radius of that circle. It's the diameter of the circle. So that would be 34 meters. And you find that the speed at the top is 17.7 meters per second when you plug in all those numbers into our equation here. Oh, and by the way, we'll assume that the roller coaster car started from rest. We'll assume that this V initial is 0. but this still works even if you start out with some non-zero speed at the top. And then at the bottom of the loop, y final is 0, your ground level. You plug in those numbers, and you find that that speed is 31.3 meters per second. So now we have this super powerful technique that allows us to ignore all the details about the shape of the path taken. All we care about is the initial configuration of the system, the final configuration, all the details in between get automatically taken into account somehow, and we can just find the answer directly. Turns out there's really deep mathematical reasons why you can ignore all those details for conservative forces, but you need to take 3 semesters of calculus to understand those mathematical reasons.